All righty, let's see. How could this go wrong? Well, let's go through an example perhaps on this. So let's say do the volume that is created by taking these curves. So take y equals x, y equals 3x, and for x from, let's just say from 1 to 3, and then spin it around the x-axis. So if we draw the picture, y equals x is our usual friend here. Y equals 3x is steeper. So let's see if I can, 1, 2, 3, 2.
So I was actually gonna I actually wanted to ask you about certain formulas in general, certain kind of or specific formulas or specific functions that can't be possibly work this way. For example, what if you had a rectangle instead, and you want to find a formula for a rectangle? If you had a few functions that could kind of resemble something like a rectangle, and you use them around when they just equate to a cylinder.
Yeah, in that case, you probably wouldn't even want to use the if you just took a rectangle and you spun it around, you would just get like, it's truly just a cylinder. So if this was like 5 and this was 2, then this height would be 2 and the radius would be 5, and then you just use the volume formula for a cylinder. Need the equation. The thing that I was saying that could go wrong here is on this one. So now you want the area that's, we have x equals 3x, y equals 3x, we've got y equals x. You want to go from 1 to 3. So here's 1 and here's 3. We're talking about that area right there spun around the axis. So what does that even look like now? Well, so take this region and spin it around this axis here. This becomes a circle. This becomes a circle. Everything becomes circles. Ah, too big. We have another big circle on the end. So it's got, volume is kind of like this outside part, and you have a hole down the middle. Just going to turn that off for a second. So the thing is it's got a hole in the middle. It's kind of supposed to be kind of like a cone, but you chopped off the top and then you drilled a slanting hole down through the middle. So the problem is if I tried to make, change color here, if I tried to do this idea where I took my disc and I spun it over here, then it wouldn't be a disc anymore because there would be a hole in the middle of it. So basically I get a disc with a hole. But just like you did, hopefully if you did the homework, all you need to do is think of this as 2 volumes, one taking away the other. So it's kind of like the volume using the y equals 3x, take away the volume using x, y equals x. You could spin the big one and get you can get like a cone with the top chopped off. And then you can do the inner one, which is like a different cone with the top chopped off. Subtract those two volumes, and you'll get the volume of this weird kind of shape. It's like a drilled out, diagonally drilled out cone that's been truncated off of the top. So the picture is actually sort of harder than the actual equation, is that the volume using the 3x will just be pi times the integral from 1 to 3 of 3x squared, because the radius function is 3x, minus the volume from 1 to 3 using x. And that's it. So in this case, it's just the difference between the two volumes. In the book, it gets tired of writing these things twice. So in the book, they actually just recombine it into one integral. So they're both the integral from 1 to 3. So I can put in 3 minus x minus the 3x squared and x squared, like that. So this is kind of like what they call the big radius, and this is like the little radius on the inside. You can see if you want here, then like the big radius is all the way out, whereas the little radius is the one in the middle. So it's like the big function minus the small function. And you know, that's not hard to work out. So I think you can probably look that out. But that's the difficulty, is if you have holes on the inside of these things. That is one. And the other is well, what happens if you revolve not around the x-axis, but you revolve around the y-axis instead? You know, you can do that. You can take your thing, you can spin it around, and it will create a volume for sure. But we can't use the exact same thing we did, because what happens is the radius and the height get reversed. So instead of the radius being up and down and the height side to side, now it's the reverse. The radius is left to right and the height is up and down. So maybe not too surprising that the volume equations, instead of dx, will have to become dy, and functions y equals f of x, you're going to have to convert over to functions x equals g of y. Just like you did in the homework, you're like, well, why do I have to do this in sideways? The answer is, well, in this section, if you do the revolution around the y-axis, you have to convert everything to turn your head sideways, left to right, instead of top to bottom. So here's what I mean for example here. Let's see. So revolve the triangle with vertices at 1, 1, 2, 1, and 2, 3 around the y-axis, and then find the volume. So it's still going to be the idea where you do pi times the radius squared. It's just, instead of being in terms of x's, it's going to be in terms of y. So let's draw the picture here. So I go 1, 2, 3. I want to take 1, 1, 1, 2, 1, and 2, 3. And you take that triangle, and you want to spin that whole thing now around the y-axis. So take this and do your spin this way. So if I do the revolution of this, the actual, what does it look like? Well, let's see. So we've got one, we've got a triangle. We're revolving that around, so now we get sort of circular shapes this way, circular shapes this way. You get a slanted So this mirror image on the other side, you get a slant that way, you get a slant that way. So it's I'm trying to connect some of these things up. All this other stuff is on the inside. So again, it's kind of, now this is kind of like a cylinder, and then you drill this sort of like diagonal thing out of the middle of it. So it's going to have a hole. If that's hard to see, this is actually going to, this is on page 367. I might be able to just pull that up. But, you can also do that as well. This is the example from page 367. That, what do you call that? Some kind of like stadium or something. Anyway. So now in this case, the big radius of any sort of like piece here, the big radius is going to be from the axis out to the far side, and the little radius is going to be from the axis to the inside. So the volume in this case will be pi times the integral. Using the formula from the book, it's the big radius squared minus the little radius squared. The only catch now is that everything is in terms of y, and so these will be like the y bounds c and d. And again, it's still pi r squared, the big one minus pi r squared, the little one, in order to eliminate the holes. Just like two volumes subtract from each other. So that's the formula. In this particular example, we need to know what these equations are. We need to know what the bounds are. So hopefully you can see that the y values are going between 1 and 3. And so I have pi 1 to 3 on my bounds there. The big radius, well, I need to know what the equation of that curve is, and I need to know the equation of that curve. So those two things are lines. This line here is straight up and down. So that one there, that's just, you're 2 units out. So x is always 2. So that's like my g. It's a little strange whenever you have a constant, because x equals 2, like that's a point, right? Well, in 1D it's a point, but in 2Ds it's this line. So x equals 2 is the big radius out, no matter where you are. You go 2 units out, 2 units out, 2 units out. What's the equation of this line here? Well, you get the line, the slanty line. I normally do it as y equals mx plus b. The problem is I don't know what b is anymore. This does not come down and hit the axis, so you're going to have to figure out the slope. I think the slope is not too hard. The rise is 2, and the run is 1. Now, I'm just going to skip over this part and just go straight to the line in terms of x. So if you do that the other way, you might not be used to this, like y equals mx plus b, but if you unravel it, you can also do y equals a different slope times y plus the x-intercept. So you can change the intercepts from y to x. The slope, instead of doing rise over run, if you flip it, it's now run over rise. So this run is 1, the rise is 2, so that would be 1/2 y. If you follow this back here, so that means it's a slope of 1/2 as far as x is concerned. So that means if you go run over rise, so if you go over 1, you go down 2. And so you actually would hit down here on the y-axis, but on the x-axis, you actually hit like right in the middle there. So the x-intercept is 1/2. And that's something you're probably not used to doing too much, finding y equals mx plus b in terms of the x equals my plus b, where it's a different intercept and a different slope. But anyway, not too bad. But as far as the formula is concerned, it's the difference of two things that are each squared. The big radius is whatever the biggest distance is from the revolution line out to the edge. And no matter where you are, that's exactly 2 units out. to get that big one. To get the little one, I come out and I hit the line. So the line will specify what that is. So that'll be 1/2 y plus 1/2. And so that's the setup. And I know it takes a little while to like turn your head. And so you have to sort of 3D orient yourself in this. But if you could figure out that this is the big radius, little radius, and work it out, that's fairly helpful. It'll be very helpful when we talk about.
So, I'm sorry, so why is the lowercase r in this case 1/2 y plus 1/2? I don't understand that aspect. I understand why capital R is 2, but why is lowercase r?
R is the distance from the axis to your object that you're revolving. And every time you go from the axis out, what's the first thing you hit? The first thing you hit is the line. If you're here, you go over, you hit the line, you hit the line, you hit the line, you hit the line. So the little radius at the top is 3, but then it shrinks down to 1. So it depends on where you're at, which means in order to figure out what a specific inner radius is, you're going to have to use this line. And therefore, the radius function is the line itself. That's
Okay.
Yeah.
I kind of get it, but not entirely.
Okay. Well, we'll do examples. We'll do more examples with this. Let's just go ahead and work this one out. It's not too bad. So this is 4. When I square this out, it'll be minus 1/4 y squared. And I will get minus 1/2 y, and I will get minus 1/4. So square it all out and then apply the negative to each term. And then maybe recombine the 4 and the 1/4 here. So that's minus 1/4 y squared minus 1/2 y. The 4 and the 1/4, that'll be 15/4. This 4 is 16/4. Integrate all of this, guys. Y cubed over 12. So it'll be y cubed over 3, but there's already a 4 there. Integrate this one, it'll be y squared over 2, but there's already a 2 there, so that becomes 4. And then 15/4 y. Plug the bounds in 1 and 3, multiply all those things by pi. So make sure we get all the pieces in there. So plug in 3, work it out. Plug in 1, work it out, subtract, multiply by pi. I don't have enough room to fit it all in. But it's just keeping track of the fractions, combining them properly. And you'll get 10 pi over 3, again, units cubed, whatever that unit is. Okay, so like I said, doing lots of examples here before my voice gives out. Let's do more examples. So here we go. So for example, let's just go ahead and do this another triangle, but an easier one. Maybe an easier one. 1, 1, and let's put this at 1, 2. I'm going to put this at 2, 1. Take this triangle here, and we're going to revolve this around a bunch of different axes and see what the different pictures end up looking like, and go from there. So we want to take this guy and revolve it around some things. So here's the revolution things. Part A, let's revolve it around the x-axis. So revolve it around the x-axis. Take this guy, spin it, and what does the shape look like when you spin it? Well, it's going to look like a cone, except you chopped out the middle of it. If you took a cylindrical, look like a cylindrical cut out of a cone that has its top chopped off. So that's what the shape looks like. Let me get one more. So a cone drilled out through the middle. So in this case, the axis is down the middle here. The little radius will be whatever the distance is up to the thing. And then the big radius will be whatever it is out to the outer one. So maybe I should try and draw them in the picture, but it's a little bit hard. So let's come back to the original picture and see where that is in this picture. So the little radius is whatever the distance is inside the hole. And the big radius will be whatever the distance is, but it'll be a different answer depending on where I am on that line. So the little radius will always be 1 unit, but the big radius will depend on where I hit that line on. You can see at one end, it's 2 units, and on the other end, the big radius is going to be 1 unit, and it's going to decrease as you go along. So the big radius function will be, we'll figure out what that is. The little radius function is always 1. It's always 1 on the inside. It's cutting on a cylinder. So to figure out what this big radius is, I need to know what the equation of this line is. So how do you do an equation of a line? Well, you got to figure out the slope. And the slope is rise over run. So I go down 1 and over 1. So I know that the slope is -1. So I have negative x plus the y-intercept. In this case, if I go over 1 and up 1 and over 1 and up 1, then I'll hit this exactly at 3. So if you extended the line back, the y-intercept would be 3, and therefore we can get the equation y equals -x plus 3, or x minus, or 3 minus x, either way. So the big radius will be governed by that outer line, -x plus 3. And if you can figure out the big radius and the little radius, then the formula is just the volume will be the integral from 1 to 2 of the big radius minus x plus 3 squared minus the little radius, which is 1 squared. And I'm not going to work out all the algebra, I'll just tell you the answer. 4 pi over 3 units cubed. So that volume of that shape that you got by the volume is 4 pi over 3. That's the first one. How about the second one if I revolved it around the y-axis? Well,
Wait, did you involve the -1 because it's elevator 1 from the x-axis?
it's 1 unit off, yep.
Okay, but and why is it a minus instead of plus? I'm just curious.
What's the formula say?
Never mind. Sorry.
You're taking away a volume.
Okay.
So really, if you just did this first integral by itself, forget the rest, just -x plus 3 squared, what volume would that be? It would be the entire filled in, it would be like a cone, like the whole thing, the whole cone.
Oh, okay.
Second volume is just that little cylinder hole that you cut out of the middle. So really, we're just taking the entire cone that's had the top chopped off and subtracting out a drilled hole down through the middle. And that's what those two, that's the reason why it's a subtraction. I don't know if that helps or not. But, all right, for the y-axis, I want to take my object, I want to spin it around the y-axis. So I get sort of like mirror image on this side, and I get little circles. And you might be like, well, wait a second, isn't that the same thing, just turned sideways? And the answer is, for this particular one, yes, because it's a symmetric shape. It's 1 unit wide and 1 unit high as the triangle. So if I revolve it, I get exactly the same shape. I don't know if it looks like it, but it's just because the scaling is kind of off here. But it's the same object, just turned sideways. So I better get 4 pi over 3 as my answer, because it's the same shape. So it better have the same volume. But in order to make sure I can set this up this way, what I have to do is come back here to my picture, and I have to do now, where's the big and little radius in this picture? Well, the little radius is the inside. The big radius is whatever it is to get out to the outside. And that'll change because it's a slanted outside. But if I bring it back to the picture, the little radius is here, and the big radius is right there. So the little radius, in this case now, is always 1 again. But the big radius is going to be a function. The only problem is I can't write it as negative x plus 3 because I want this one now to be in terms of y. Because I know that this integral volume will be the integral of something squared minus something squared dy. Because all of the h's are now horizontal instead of vertical. So everything has to be y numbers. Maybe even just real quick, we can see that the bounds on this particular one are still 1 to 2. It's like 1 to 2 for x and also 1 to 2 for y. That's just a special case for this one we're doing. So the y bounds are still the same as the x bounds, but that's just because of the symmetric nature of the object. The big and small radius, again, big and small here, are going to be in terms of y. So little r doesn't care because it's a constant. So I can put that in as 1. But what is this line if I convert it to y instead of the original, which is x? So I have to convert here. I take that line, which is y equals negative x plus 3, and I need to convert it into x equals something. So if you convert that by basically just solve for x, hopefully you can see it's not too bad. If you bring the x over, it becomes positive. If I bring the y over, it becomes negative. So I get negative y plus 3. And that will be my big radius. So it's just figuring out which curve is the big radius and which curve is the little radius. In a lot of these problems, if you accidentally switch them, all that matters is your answer will be negative. So you're like, thank goodness, if I do the homework wrong by putting these things in the wrong order, I'll get the negative answer, and that should be a problem because these are supposed to be true volumes. So anyway, that's the big radius, and so I can then substitute that in minus y plus 3.
So I'm just curious, so how can you exactly determine where to place the capital R exactly, or where should you place it? How can you really determine that?
I'll draw another picture on the next page, and then you can tell me.
Okay.
All right. So look at these two integrals. What's the difference? The only difference is I'm using a different letter to do the integral. It doesn't matter if I call it x or I call it y. When I integrate all this up and put the bounds in, I will get 4 pi over 3. Well, I get the same answer, 4 pi over 3 units 2. I want to come back to this example, but to answer your question, let's try it. Let's just try a picture where I have a function up here, and I have another function down here. I'm just going to make it hit. And I want to take this region right here, and I want to revolve it around the axis. You just even get rid of, I don't know if I can just forget that part right there. So we've got another function. I want to revolve this thing around the axis. So I've got one function up top, F1, and I've got another function at the bottom. What does this region look like if I were to revolve that around the axis? Well, it's not necessarily pretty, but if you think about revolutions, it's kind of like take your shape, make a mirror image of it on the other side, and then connect everything with circles. So that's going to be a circle. That's going to be a circle. The stuff on the inside, I'll use dotted lines. And the stuff on the outside, I'll use like solid lines. So, I don't know, some kind of weird vase that has a hole in the bottom of it. But anyway, when I revolve this, all of these things are going to be circles. And so the little radius is going to be the inside, and the outer radius is going to be the outside. So little r and big R. So come back over here. Which of these two functions is the little radius, and which one is the big radius? Kyle?
The big, okay, so I'm gonna say the big radius is gonna be the one that's close, the one that's farther away, or
Yeah.
that it's farther away, and the short one's gonna be the one that's closer to it, but so closer to the x-axis. But I'm just curious because depending on where on the function or x-axis you put that large r, it can determine whether it's longer, shorter, that kind of thing.
Yeah, so I know that the big R is going to be one of these two functions and the little r is going to be the other one. So which one goes with big R?
Big R is gonna be the one that's farthest away.
So which one is it?
F1.
Correct. That's F1 and that's F2. So little radius is there, big radius is there. That's
Cool.
it. That's it.
But what's that?
You have to draw the picture. You have to.
Okay. No, I understand that. I understand that aspect. But I'm understanding like what happened. What's stopping you putting R, the larger R, F1, like onto the right of R, of lowercase r or F2, when that results in having a short area? Like, if in order to really matter where you put it.
What would that even mean geometrically?
I'm not entirely sure. It just feels like that R plays a critical role, and it just seems as if, depending on where you put it on the x-axis, again, determine whether that R is longer or shorter than necessary, or that's what I'm thinking about here.
Well, I think you're just going to see cases where it's going to be clear that the larger R is the one that's furthest away from the axis, and the little r is the one that's closest. I'm pretty sure that's all we're going to end up seeing.
No. Yeah, again, yeah, that's part of understand. I just, because the function kind of increases and decreases over time, the F1, and so depending on where R is on the axis, that could result in the R length being shorter or longer than it was relative to its previous location.
Oh, so right at the beginning here, truly like the very beginning little radius is small, and the very beginning big radius is really big.
Yeah.
In the middle, the little radius is getting bigger and the big radius is getting smaller. And even really what's happening here, the big radius and the little radius are the same.
Oh, okay. So it's just relative to the small r. Okay.
And that's why it's a function of x. So it depends on which x you pick as to what those actual values end up being.
Okay. Okay, I understand.
Okay. Right. Okay. So back to that example that I had here, because I'm going to want to introduce one more possibility where, let's see, this is 1, 1, 2, 2. Take my triangle. I already know that the equation of the top of this is y equals negative x plus 3, or if you prefer, it's x equals negative y plus 3, if you're looking left, right, or up, down. So now instead of revolving it around the x-axis or revolving it around the y-axis, I want to revolve it around the line, it's line x equals negative 1. Why would you want to do that? Well, it's math class. So here's the x-axis. X equals negative 1 is down here. So I want to take my object and I want to revolve it around this line now. So instead of revolving it around the x-axis, I'm now like moving down and revolving it here. So what does that shape now look like? I'll take my thing. I'm coming down. Here's the x-axis. Here's the line that I really want. Keep going down, do a mirror image way down here, and now put in my circles. This one should have been a dotted line. It's hard to undo. So I just get like a really, it's like an even longer, whatever that shape was I had, it's like a cone with the middle drilled out. It's still kind of like that same thing, except it's like a much wider cone. Yeah, it's a much wider cone. But the only difference is I just changed my big radius and I've changed my little radius. And how have I done that? Well, the old radius was little r was here and big R was to the line. That's the old ones. And now the new ones is what's the difference is I've added one more unit onto each one. So now the little radius is just one more unit and the big radius is just one more unit off. So I can adjust the old example. Let's see, what was the old one? I just revolved this around the x-axis. The setup was pi 1, 2, negative x plus 3 squared minus 1 squared. That was the old one. Now I can adjust by just taking R1 and adding 1 to that, and take big R and adding one more unit onto that, because that's all I've done is I've just increased the unit by 1, the radius by 1 unit. And now the new volume will be pi negative x plus 3, but then I add one more unit onto it before I square it. So that's like the new big radius. And the new little radius will be, it's the old one, which is just 1, and now the new little radius is, that's the new little r. I just jacked both of them up by 1 unit, and then I get that integral instead. So that looks like the integral from 1 to 2 part of pi. And then it'll be negative x. I can combine those to get 4 squared, and then minus 2 squared. And that new volume there, if you're curious, you can work it out, multiply everything out, or do a u substitution, or use chapter 6, and you'll get 79 pi over 3. So the old one was 4 pi over 3. By jacking it up like this, it changes the volume rather radically. So that's crap. It's not even the line y equals -1. What line is this down here? It's not x equals -1. I'll be sitting there going, that's an idiot. That's the line y equals -1. So the line y equals -1. Actually, I'm not sure. No, that's not even the right answer. I've got this reversed. I don't know what that one is. I didn't actually work that one out on my piece of paper. I should have done that. Didn't too many of these other ones, but not that one. Ooh-wee. Well, how about this? Left to the students figure out. That's what professors do if they don't want to work it out and they're too lazy. You just say, you guys go do it. You can do this. It's not hard. Multiply it out, work this piece out. Yeah, I don't think it's going to jack it up by a factor of 1. But that's the deal. It's either, look, you just have to figure out where the big radius is, and you have to figure out where the little radius is, and then you can just put these things together into a formula. So that's called the method by disks, or when you do these disks here, previously they looked like disks, but now they have a hole in the middle. So you can either have a disk, which is fine, but if you take a disk and you knock a hole in the middle of it, then each of those things will look like that. So if there's a hole in the middle, it's not a disk anymore. It's go to the hardware store. It's a washer. So this section is actually called like the disk or washer method for doing that volume. And it's just the big R minus the little r. Once you determine what the big R and the little r are, then you're going to be in good shape. That's 7.2. I think I'll probably blend 7.3 partially now and partially on Monday, depending on how far we get, because that's kind of a lot to do all at once. But let's take another quick break, clear the palate, get a drink, and then we'll be back at say 11:12, and we'll finish this puppy off. See you in a few minutes.